Good day. For those of you who do not know us, we're the instructional staff for ASCII 150. Professors Hiran Patel and Werner Dietl and Douglas Harder. In this topic, we're going to introduce the concept of loops and specifically a for loop. In this lesson, we are going to introduce the concept of a repetition statement and specifically a for loop which iterates from one point until another. We will look at an example where we actually use the looping variable. We will author a program that determines if an integer is prime. We will then consider the different variations of a for loop and look at 3 different examples of using a for loop within a for loop. Now, suppose you want to execute a particular action or sequence of statements a fixed number of times. This can be performed with a repetition statement. Specifically, in this case, we will look at a for loop. Now, when this program is executed, the output is very simple. It will print the word hello exactly 10 times. Once the 10th printing occurs, the program will exit. So let's take a look at how this for loop works. Let's take a closer look at the for loop. As you can see, the for loop appears similar to the conditional statement. However, instead of the keyword if, we see the keyword for. Between the parentheses, rather than just having a single condition, we actually have 3 expressions separated by 2 semicolons. The first expression is the declaration of the loop variable and its initial value. So in this case, k is being declared to be of type int, and it is initialized with the value 1. The next expression is a condition. That condition will be tested, and if it evaluates to true, then the loop body is executed. Whenever that expression evaluates to false, we carry on executing at the end of the looping statement. So we stop performing this loop. However, each time this condition evaluates to true, the loop body is then executed. In this case, it just prints the word hello. Now, at this point, k is equal to 1, so therefore k will always be less than or equal to 10 unless we do something else. So this brings us to the third component of the for loop, and that is the update statement. The update statement is executed after each execution of the loop body. And in this case, the update statement is nothing more than increment the value of k. Let's actually work through this example to see what's happening a little bit beneath the hood. So, the first thing we do is we declared the loop variable k. K is initialized with the value 1. Now, k is stored somewhere in main memory. We'll discuss that later. But right now, that location in main memory is storing the value 1. Then we carry on and we check, is k less than or equal to 5? Yes, it is. And so we execute the loop body. That prints hello. At the end of the execution of the loop body, we then execute the update statement, which is increment k. So now k is equal to 2. We check the condition again. 2 is less than or equal to 5. Therefore, we execute the loop body. Having executed the loop body, we increment the value of k. 3 is less than or equal to 5. We execute the body. We update the value of k. 4 is less than or equal to 5. We execute the body, and we update the value of k. 5 is less than or equal to 5, So we execute the body and we increment the value of k. At this point, 6 less than or equal to 5 evaluates to false, and the loop stops executing, and we carry on executing any statements that appear after the end of the closing brace of this for loop. Now, very importantly, we can actually use the looping variable inside the loop body. So in this case, rather than printing hello, we will just access and print the value of k. So once again, k is initialized to 1. We test the statement, it's true, so we execute the body. We print the value of k. Update the value of k, the condition is true, we print it, update the value of k. Test the condition, it's true, execute the body, update k. Test the condition, true, execute the body, update k, and so on and so forth until the condition fails or returns false, and we carry on executing after the end of the for loop. We can use a for loop to perform various calculations. So for example, here we're calculating the sum of k equaling 1 to 5 by initially declaring a local variable sum, which is initialized to 0, and then we will add to that value sum 1, then 2, then 3, then 4, and then 5. So as before, sum is initialized with the value 0. We will now perform the looping statement, and we initialize k with the value of 1. K is less than or equal to 5, so we execute the loop body, and so we add the value of k to sum. We update the value of k, test the condition, still true, k is less than or equal to 5. We execute the loop body, which adds the value 2 onto sum, so now sum is equal to 3. We increment the value of k. 3 is less than or equal to 5. We execute the loop body, which adds the value of k onto sum, increment the value of k, test the statement, it's true, execute the loop body, which now increases the value of sum to 10, increment k, the condition is true again, we execute the loop body, that increases the sum to 15, and we increment k, and once again the looping statement or the condition evaluates to false, and therefore we are finished the for loop. Now we carry on executing. The very next statement is a print of the value sum. Now, as you recall from secondary school, we can calculate the value 5 factorial by multiplying 5 times 4 times 3 times 2 times 1, which is the same as 1 times 2 times 3 times 4 times 5. So what we will do here to calculate 5 factorial is we will initialize or declare a local variable factorial and initialize it with the value 1. We will now run this looping statement, which will execute 5 times. The looping variable will take on the values 1, 2, 3, 4, and 5, and each time we will auto-multiply the local variable factorial by that looping variable. So, k is declared and initialized to be 1. K is less than or equal to 5, true, so we multiply factorial by 1. Well, I think we just wasted our time, but c'est la vie. We then increment the value of k. The condition is still true, k is less than or equal to 5, and therefore we multiply the local variable factorial by 2, and therefore factorial is now 2. We increment the value of k at the end of the loop body, so now k is equal to 3, the condition is true, we now multiply factorial by 3, which is 6, and after the loop body has been executed, we increment k. The condition is true. We multiply factorial by 4, giving us 24. We increment the value of k. We test the condition. It's still true. So therefore, we multiply factorial by 5, giving us 120. And at the end of the loop body, we increment k one more time. Now the condition is false, so we exit or finish the for loop. And now the next statement is to print the value of factorial. So that is the output. Next, as another application of a for loop, let us determine if an integer n is prime. Now, by definition, a positive integer n is prime if it is divisible only by 1 and n. In other words, n is prime if it is not divisible by all the integers going from 2 up until n minus 1 inclusive. Now, if n is divisible by an integer k, then the remainder of n divided by k, when using long division, is 0. In C++, we find the remainder of n divided by k by calculating n modulo k, using the modulus operator or the remainder operator. Therefore, this sounds like something we can do with a for loop. We will test if n modulo k is equal to 0 for every single value of k going not from 1 to n, but from 2 to n minus 1. Let us implement this in a program. Here we have a local variable n declared to be of type int, so an integer, and it's initialized with a default value. It doesn't matter because we're going to query the user to enter an integer, and that integer entered by the user will be assigned to the local variable n. Okay, so how are we going to record whether or not n is prime? Well, if you were doing this, you'd assume n is prime, and then you'd start dividing n by 2, then 3, and so on and so forth up until n minus 1. And if you ever come across a k such that n modulo k is equal to 0, that is, n is divisible by k, then you may assume that, or deduce, that n is not prime. Okay, so let us start by assuming that n is prime. We will have a local variable is prime declared to be of type bool. That is, it holds the value true or false. We will initialize it now with the value true. We are assuming that n is prime. Now, once we run our test, we will then check this local variable. If is prime is true, then we will print a statement indicating that yes, the integer n is prime. If, however, we ever find that n modulo k is equal to 0, that is, n is divisible by k, then we will assign the local variable is prime a value of false. So if is prime gets assigned the value false ever, then when the condition is prime is tested, is prime has the value false, so we will execute the alternative body, and that prints the statement that the integer is not prime. All right, so here is our for loop. This for loop will run with k being initialized with the value 2, and the condition will be as long as k is less than n. The last time k less than n is true is when k is equal to n minus 1. Now, this for loop is exactly the same as the for loop you see over here, because k and n are both integers, so the condition k less than n is equivalent to asking if k is less than or equal to n minus 1. So you could choose either one, and either one would be equally correct. However, for reasons which you will see later, we're going to assume that we will use the condition k less than n. All right, so now we're looping from k equaling 2 all the way up to n minus 1. Each time the loop body executes, we will check if n modulo k is equal to 0, that is, n is divisible by k, then we will set the local variable is prime to be false. So this program will test if n is divisible by k for every value of k going from 2 to n minus 1. If it is ever found that n is divisible by such a k, then we will set the local variable is prime equal to false, and at the end of this for loop, if we never updated the local variable is prime, then the integer n must have been prime. Now, in the previous program, we found the remainder of n divided by k for all values of k going from 2 to n minus 1. Now, do we actually have to test all integers from 2 to n minus 1? Well, suppose we found that n was divisible by 14. Well, 14 is not prime, and 14 is equal to 2 times 7. So if n is divisible by 14, then n must also be divisible by either 2 or 7. And if n was not divisible by 2 and not divisible by 7, it could also not be divisible by 14. So from this, we can therefore conclude it is only necessary to test if n is divisible by all prime numbers between 2 and n minus 1. All right, that's significantly less work, but we have a problem here. At this point in time, we do not have a list of all prime numbers between 2 and n minus 1. However, we do know that all multiples of 2, or all even numbers greater than 2, are not prime. So, can we avoid calculating n modulo k for all even integer values of k? Sure, let's try that. Here's our strategy. We're going to test if n modulo 2 is equal to 0. If it is, it's not prime, because therefore it's divisible, and we're done. However, if n modulo 2 is not equal to 0, then we will go on and test if n modulo k is equal to 0 for all values of k starting at 3, then 5, 7, 9, and so on, all the way up to n minus 1. Now, we could use the following condition statement and for loop. So first, test if n is divisible by 2. If n is divisible by 2, we know that n is not prime, so we will just set the local variable is prime to false, and there's nothing else to check. Otherwise, we will have a loop that runs from k equaling 3 all the way up to n minus 1, but we will only test if n is divisible by k for odd values of k. Well, k is odd if k modulo 2 is not equal to 0. So if k is odd, Then we will test if n modulo k is equal to 0. If it is, we will then set is prime to be false. All right, but that's sort of useless. We're still calculating modulus twice. Let's take a look at this statement here. Plus plus k, that's the only thing we've used up until now. But from the previous talk on assignment operators, you know that plus plus k does exactly the same thing as k plus equals 1. So instead of having plus plus k there, we could include the statement k plus equals 1. But if we can include k plus equals 1, could we just not have k plus equals 2 instead? So now we have a for loop that starts with k being initialized with a value of 3, and then each time k is updated, so each time the body of the loop is executed, we will then perform the operation k plus equals 2, not k plus equals 1. So k is initially 3, we execute the loop body, and at the end we add 2 to the value of k. So now k is 5. And again, we test if n modulo k is 0, and at the end of the loop body, we increment the value of k by 2. So now k is equal to 7, and so on and so forth, so long as k is less than n. So now we have a simpler program, one that tests only approximately half as many integers to determine whether or not n is prime, because we are no longer testing if n is divisible by any even number other than 2. Now here we have a different example. It's similar to the previous example where we calculated a sum. However, now the update statement is not an increment, but an automatic multiplication. So each time the body loop is executed, then k will be multiplied by the value or integer 2. Let's take a look at and see how this will work out. So initially we have a local variable sum, which is initialized to the value 0. We then execute the for loop. A local variable or looping variable k is initialized to the value of 1, and k is less than or equal to 20, so we execute the loop body, which adds 1 to sum. Sum's now equal to 1, and we execute the update statement, which multiplies k by 2. K is still less than or equal to 20. We execute the body. That adds 2 onto the sum, which is now 3, and we multiply k by 2. The condition is still true, so we execute the body, adding 4 onto 3 to give 7, and we multiply k by 2. The condition is still true, 8 is less than or equal to 20, so we execute the body, we add 8 to 7 to give 15, and we multiply k by 2. Once again, the condition continues to be true, so we add 16 onto 15, giving sum the value of 31, and we perform the update statement. Now, at this point, the condition is false. 32 is no longer less than or equal to 20, and therefore the for loop is complete. We now print out the value stored in the local variable sum, and so therefore 31 is printed to the screen. Here's another variation on a for loop. Here we are iterating from k down to 0. So each update statement decrements the value of k by 1. So when executing this loop body, the first thing that happens is we have a loop variable k. It's initialized with the value 4. the condition is true, and therefore we print the value of k and then decrement that value. The condition continues to be true, so we print 3, decrement the value, and because the condition continues to be true, we execute the loop body again, print 2, and decrement the value of k. The condition is true, we execute the loop body, we print the value of k, and then we decrement it. The condition is true, we print the value of k, and then once again we decrement it. At this point, k is equal to -1, so the condition, -1 greater than or equal to 0, evaluates to false, and therefore we are finished. Of course, one important thing to remember is the endpoints do not need to be 0 or 1. So here is a for loop where k varies from 256 up to 1023. Here's a for loop where k starts at 256 but goes down to 129. Now, we've looked at many different types of for loops, and we can see that we can make many different variations, where they start, where they end, and how the looping variable is updated. But the most important loop you will see in this course is one where k is initialized with the value 0, and this loop will continue as long as k is less than n. So basically, k takes on all integer values from 0 up until n-1. If you prefer, you can use the following structure. Rather than having k less than n, you can also have k not equal to n. These two conditions, for the purposes of this for loop, are the same. Both of these conditions continue to be true as long as k is less than n. Now we're going to go a little bit further than just a single loop. We're now going to look at having a loop within a loop. So, given two integers m and n, we will create the following ASCII art. Essentially, what we're doing here is displaying the entries of an m by n matrix, where each entry of that matrix will be shown with an asterisk. So, to create this ASCII art, we will require a loop where each iteration of that loop will print one of the m rows. Well, this outer loop must therefore run from 1 to m. Now, each time the body of that loop executes, it must print all the asterisks in one row. That means we must print n asterisks. This is of course also going to require a loop, but now that inner loop is going to run from 1 to n. Once we've printed all of the asterisks in a particular line, we must then print an end of line so that the next row can be written on the next line of output. So here we see our program. We have two local variables, m and n, and we prompt the user to enter each of those integers. We will then have a loop where we have a loop variable called rows. So rather than using I, j, or k, we're specifying that this loop variable is associated with the printing of each of the rows of this matrix. And of course, it runs from 1 until m. Next, inside that loop, we have to print all of the asterisks in that line. So we must have a loop that runs from columns equaling the value 1, or assigned the value 1, all the way up until the number of columns is n. So each time we run that column, we will print a string where the first character in that string is an asterisk and the second is a space, and that will nicely space out the asterisks in that line. Now, once we've printed out all n asterisks in that one line, we will then print an end of line. All right, now here's a different loop. I'd like to essentially display this square matrix where the only entries that are being highlighted with asterisks are the entries on or below the diagonal. So the lower triangular entries of that matrix. So how are we going to do this? Well, you will notice that in row 2, we should only print column 1 and column 2. Also, in row 5, we should only print an asterisk for row 1, 2, 3, 4, and 5. So therefore, we could do this by including a conditional statement in the inner for loop. So we will only print an asterisk followed by a space if the column we are in is less than or equal to the row that we are currently in. So initially, row is equal to 1, and consequently in the inner loop, columns is equal to 1 only once, and so only one asterisk will be printed. All right, that's not bad. However, note, in row 1 we print 1 asterisk. In row 2 we print 2 asterisks. In row 3 we print 3 of them, and so on and so forth. So could we not change the ending condition of the inner for loop as we go through? So here we see a situation where the halting condition, or the condition for the inner for loop, is that columns is less than or equal to rows. Now, remember that rows starts at 1, and with each iteration or execution of the outer for loop, rows is incremented by 1. Now, columns will start at 1, and initially when rows is equal to 1, the condition will be columns less than or equal to 1. On the next iteration of the outer loop, rows is equal to 2, and so once again, the inner loop will go columns initially assigned 1 continues as long as columns is less than or equal to 2. So on the second row, this will print 2 asterisks, and so on and so forth. Next, let us consider this piece of ASCII art. Here we are highlighting the diagonal entries of an n by n matrix with a lowercase o, and all of the strictly upper triangular entries with an asterisk. Well, at this point you should realize that we do have to print something for every single entry of this matrix. So we're not going to be able to just change the terminating conditions, because in the first row there are no spaces before the first O. In the third row there are a number of spaces, well, technically 5 or 4 before the first O, and in the fifth row there are 8 spaces before the first O. So now we're back to the inner and outer loops going from 1 to n. However, inside the inner loop, we will now have a cascading conditional statement. So first we check. If columns is less than rows, we're below the diagonal, and therefore we will simply print two spaces. If columns equals rows, that indicates we are on the diagonal, and so we will print a string containing an O and a space. And the only other possibility, the alternative, is that we are in the upper triangular component, and therefore we will print an asterisk together with a space. Once again, once we've finished printing the entire row, then we will print an end-of-line character to continue printing the next row of the matrix. Now, these sound a lot like silly little games because all we're doing is printing asterisks and lowercase o's and spaces. However, all of these algorithms are essential for implementing algorithms associated with linear algebra. For example, initializing the entries of an n by n matrix requires two for loops. Multiplying an n-dimensional vector by an m by n matrix will also require a similar loop within a loop. Performing Gaussian elimination will actually require a loop within a loop within a loop. Similarly, once you have the system in row echelon form, calculating the solution using backward substitution will require a loop within a loop, and multiplying an L by M and an M by N matrix will require, again, a triply nested for loop.